So today we're going to discuss the spin of an object and how its accuracy is increased during flight. So our observations are going to be pitching and yawing, along with the madness effect and the drag. During our analysis, we'll discuss the factors that come into play when observing the moving object. These factors will point out the differences between a spinning or a non-spinning object in our hypothesis.
Now, a round cannonball is stable whichever way it's flying through the air, but an elongated projectile has to be spun to keep its stability in flight.
So how could a projectile be spun? Someone came up with a groovy solution. Literally, this is what's called a rifled barrel.
And what the rifling does, these grooves down the barrel, is actually impart spin to the projectile as it travels.
When the projectile is fired through a rifled barrel, it grips the grooves as it moves forward and starts to spin. This gives it gyroscopic stability and a massive improvement in accuracy.
From the video you just saw, you could see that a bullet with a rotation on it causes it to be more accurate. One force that comes into play is the Magnus force, and this is due to a crosswind as the bullet is going through the air. The Magnus force plays a significant role in the bullet stability. The force acts at either the center of pressure instead of center of gravity. If the center of pressure is ahead of the center of gravity, then the Magnus force acts as a destabilizing force. If it is behind the center of gravity, it acts as a stabilizing force. And as you can see from the equation, Fm is the Magnus force, S is the air resistance coefficient, and W is the angular velocity, and V is the velocity of the crosswind. And that angular velocity and the velocity of the crosswind is a cross product, so it either gives you a force up or down depending on the angular rotation of the bullet.
In this video, we follow a simulated bullet in flight. This first video demonstrates a bullet with no rotation. As you can see, within seconds, it has pitched downward and assumedly decelerated along the y-axis. The second video demonstrates a bullet with rotation about its axis of motion, and it survives flight by a few more seconds, ensuring both greater distance and a better accuracy. A crucial aspect to this difference in performance is the onset of a high force of drag. This is determined by the equation demonstrated right here. Here the factors are the density of the fluid, the velocity, and the cross-sectional area given. As demonstrated by the video prior, spin ensures a longer period of minimal area exposed.
During the simulation, we could see that the yaw and pitch is slowly decreasing. This is exhibiting stabilization. As I fast forward, about 170 yards down the range, we can see that the yaw and pitch is slowly becoming zero. The bullet is now fully stabilized.
The shape and spin of the bullet helps reduce the drag as seen in the coefficient of the drag equation seen below. The reduction of drag equates to the bullet traveling at a greater distance.
Not just bullets, but all objects exhibit a drag and Magnus force. We decided to use a bullet for an example because over the years, its innovation has led to a more accurate and more stable flight pattern. We can now conclude that a spinning object will have a smaller drag force versus a non-spinning object. This will contribute to a smaller pitch and yaw. Overall, an increase in stability will be observed.